solve an equation that involves the fractional part of an unknown, what we call the floor of an unknown. And you can see this equation here. It says 12 times the fractional part. Now, the fractional part's always a number less than 1. And then this says minus 3 times the floor of the number minus 7/6 is equal to the number. So it's kind of intriguing. You know, I've never done much of this when I was in college, so it's kind of fun to learn it. Now, let's spend some time on this. This inequality right here is true because we're talking about the fractional part of a number. So for example, if you had 4.7, the fractional part of 4.7 would be 7/10 or 0.7. So of course that's less than 1. All right. Now this what is sometimes called the sandwich, I guess, or the pinching result. Is it? Let's use that same number, 4.7. The floor of 4.7 would be 7. I'm sorry, the floor of 4.7 would be 4. Okay, the floor of 4.7 would be 4. It's the greatest integer that's less than 4.7. They used to call it the greatest integer function. Now it's more frequently and less ambiguously called the floor function. Now again, if x is 4.7, its floor is 4 by this notation here. And if you add 1 to the floor, you get 4 is less than or equal to 4.7 is less than 5. So this certainly makes sense right here, this statement right here. And it comes in useful in determining bounds for the floor value. Now this piece right here also is quite intuitive. It says x is equal to its floor plus its fractional part. And again, the same example. If x is equal to 4.7, the floor of 4.7 is 4, and then the fractional part is 0.7. So this is the truth right here also. Now this notation here is a little maybe obscure or exotic, but this says the floor of any real number is always going to be an integer. Now normally in our case, it's going to be natural numbers or perhaps even 0, but literally the floor function always returns an integer. And it's a mapping from the real numbers to the integers. And again, for most of the practical problems we do, it's a mapping to the natural numbers. Now, in hindsight, I actually discovered a nice little algorithm here to solve all these kind of problems. Now, it's not like I wrote this down at the beginning. I only toiled through this and spent an hour on it to figure it out. And then I realized, oh, this is going to happen every time. What's crucial right here is to see if you can get x expressed as a function of its floor. This would be the composition of two functions, right? The floor function is a function, but if you can express x as some function of its floor, that's nice because you see the floor is guaranteed to be an integer, a clean number, not a fraction. Now you probably could do this as a function of the curly braces or the fractional piece, but then you're dealing with fractions, which maybe is a little computationally a bit more of a headache, all right? So step 1 is to find x as a function of its floor. Now step 2, you can use this inequality here, the kind of this pinching inequality, if you want to call it that, to find upper and lower bounds for the floor. And then, of course, once you get the upper and lower bounds, that gives you a list of potential floors or of floors that will satisfy the conditions. And then so you'll substitute those floors in. That's what step 3. So literally, I really think this is a nice little sort of Betty Crocker way to do this. You can go through manipulations using properties to express x as a function of its floor. You can find upper and lower bounds for the floor using this inequality right here. And then once you've found those, you substitute each of them back in to solve the problem. All right, now let's take a look at how this might go. Here we go. Let's get this up in your viewing pleasure here. All right, now let's see. Now, y'all, what I did first here, notice that this says this is x. The original equation has x at the end. but we want to get this as a function of the floor, all right? So it makes sense to replace x with this expression right here, okay? If you replace x with this expression right here, at least you'll get the floor. So rewriting it like this, you have the floor at the end instead of just x, right? So we're closer towards getting this as a function of the floor. Now this next piece right here is just purely algebraic. We subtract the floor and the fractional part from both sides to get this statement right here. Again, this is just like a regular equation, okay? That's algebra there. Now, but notice we still have the fractional piece here. Now, if you go back up to this guy right here, you can rewrite the fractional piece as x minus the floor. You can rewrite the curly brace as x minus the floor. And notice that's exactly what I did going from here to here. You see we had 11 times the fractional piece or the fractional part. Well, the fractional part is x minus the floor, all right? See, and now we're making some serious progress because we are getting, at this stage right here, the problem is divide by 11 and you have x as a function of the floor, which is nice because then that way, once you find out what the ranges for the floor is, then you can substitute those values in. So let's move on along here. Now, I left it like this temporarily, but I'll show you why. We still have to determine the bounds. But if you take a look right here, this from here to here involves one step, namely dividing through by 66. All right. And so right here we have x as a function of the floor, which will come in super handy. Now, the rest of this piece, since we have the 66 right here, it makes a lot of sense. In fact, it's necessary to multiply this pinching theorem, or whatever you want to call it, this inequality, this compound inequality. If you multiply this compound inequality by 66, multiply this by 66, there's just going to be 66 all over the place. All right, so that's exactly where this came from. I multiplied what we just looked at by 66. But notice that 66 is also, 66x is given in terms of the floor. So you see how this gets replaced with 90x plus 7, folks. Again, you got 66x right here, 66x right here. We know that 66x is equal to this, so we literally substituted in there. Now again, we have a compound inequality. And this is what, if you take 7 away from 66, you get 59. If you take 66 away from 90, you get 24. That's where we get this inequality. Now notice this is where you get 0, 1, and 2. 24 times 0 is less than 59. 24 times 1 is less than 59. And 24 times 2, you see 0, 1, and 2. Now notice this doesn't contribute anything other than 0. Only negative values of x would satisfy this, right? If you picked positive values of x, you're never going to get the truth out here. So this inequality didn't do much for us. So we've determined the bounds are from 0 to 2. 0, 1, and 2, right? That's the list of 3 floors that we can try. Now we're almost done. Okay, 0, 1, and 2. That's where, if you put 0 right here, if you substitute 0 in for the floor, which is what it is, it's not x, it's the floor of x, and that's hard to get used to. But when you put 0 in there, you get this element right here, 7 over 66. All right, 7 over 66. If you substitute 1 right here, you get 97 over 66. And finally, if you substitute 2, you get 187 over 66, which actually reduces to 17 over 16. So y'all, this is pretty neat. I like this. It's very interesting stuff, in my opinion. And just to give you a little bit of insight on how surprising this was to me, I designed this problem to only have 17 over 16 as the solution. And when I was working it out, I go, what's going on? Am I making mistakes here? So when I originally designed the problem, I picked 17 over 16 as a solution and then created this the floor in the fractional part equation. That in other words, I literally created this equation knowing that I wanted the solution to be 17 over 6. And you can do that yourself. I mean, you can create as many of these problems as you want. And so I thought, okay, that's going to be the only answer, but I was super wrong. And so that's some more theory here about these things that I don't know enough about, but I learned it the hard way. So in other words, again, I'll repeat, I designed the problem to have 17 over 16 as a solution, but it turned out we got these other two answers as well, 7 over 66 and 97 over 66. Very interesting stuff. And by the way, this is a problem I made up, so I'm not sure I'm right. I'm pretty sure, I've spent like 3 hours on this thing. Pretty sure I got it right. But if any of you want to watch it and let me know if there's you see any better ways of doing it, or if you uncovered any arithmetic mistakes, I'd sure like to know. Hope you enjoyed the video.